Hey, good to have you here for this episode. Today, we're diving into a pretty comprehensive document covering magnetic sensor technologies and their applications, ranging from dairy farm health monitoring to space and automotive systems.
Yeah, it's quite a journey. We're talking about everything from biosensors detecting bovine mastitis to advanced spin valve sensors, micromechanical resonant magnetometers, inductive suspensions, ecological monitoring, magnetic levitation, and even magnetic angle sensors. It's a lot, but we'll unpack it carefully.
Absolutely. And since our audience has a solid technical background, we'll keep the discussion detailed but clear. So, let's start with something very practical. Magnetic biosensors for detecting bovine mastitis.
Right, mastitis is a big deal in dairy farming. It's an inflammation of the mammary gland caused mainly by infections, and it leads to significant economic losses due to reduced milk yield and treatment costs.
Exactly. Early detection of pathogens like Staphylococcus aureus and various Streptococcus species is crucial. Traditional methods include the California mastitis test, microbiological culture, PCR, and immunodiagnostics like ELISA.
But each has its limitations. The California mastitis test is quick but can't identify specific pathogens. Culture is sensitive and specific, but slow and sometimes inaccurate. PCR is sensitive but can't definitively assign causality. And immunodiagnostics, while rapid, require specialized training and aren't always suitable for on-farm use.
That's where magnetic biosensors come in. They use magnetoresistive sensors combined with superparamagnetic nanoparticles functionalized with antibodies specific to the pathogens.
So the idea is that bacteria in milk get labeled with these magnetic nanoparticles via antibodies. Then, as the labeled bacteria flow through microfluidic channels over spin valve magnetoresistive sensors, the sensors detect the fringe magnetic fields generated by the magnetized nanoparticles.
Right. And this approach offers high sensitivity. Some magneto-immunosensors can detect as low as 1 colony-forming unit per milliliter. Plus, magnetic detection reduces biological background noise compared to optical methods and allows rapid detection without the need for cell culture.
The document describes a portable lab-on-chip platform integrating spin valve sensors with microfluidics and electronics for inflow detection. But raw milk is a complex matrix. Fat globules and colloidal particles interfere with detection.
To address that, they add surfactants like Tween 20, heat the milk to around 60 degrees Celsius, and agitate it to homogenize the sample and improve nanoparticle labeling.
Calibration results showed detection limits around 100 CFU per milliliter for key pathogens like S. agalactiae and S. aureus. However, bacterial clustering and variable nanoparticle binding complicate quantification.
Validation with real mastitic milk samples showed moderate sensitivity and specificity compared to PCR and microbiology. Some false positives were attributed to nanoparticle agglomeration and milk matrix effects.
So strengths include effective immunological recognition and nanoparticle functionalization. But weaknesses involve quantification challenges, signal cancellation due to magnetic dipole interactions, and interference from the milk matrix.
Looking ahead, integrating pre-treatment steps into microfluidic platforms, multiplexing sensors, expanding antibody panels, and improving electronics could enable rapid on-farm diagnosis, reducing antibiotic use, and improving dairy health.
It's fascinating how magnetic biosensing can complement traditional methods, especially given the economic and animal welfare implications.
Definitely. Now, moving on to the core sensor technology behind this spin valve magnetoresistive sensors.
Spin valve sensors are a mature magnetoresistive technology widely used in biosensing and other fields. They consist of multi-layer thin films of ferromagnetic and non-magnetic metals like tantalum, manganese iridium, cobalt iron, copper, and nickel iron, with nanometer scale thicknesses.
The key principle is that the sensor's electrical resistance changes depending on the relative orientation of magnetization in the ferromagnetic layers. This makes them highly sensitive to magnetic fields.
The active sensor areas are tiny, on the order of 10 by 2 micrometers or 3 by 100 micrometers. In biosensing, these sensors detect fringe magnetic fields from superparamagnetic nanoparticles attached to bacteria flowing over the sensor surface.
Fabrication involves ion beam deposition on silicon substrates with passivation layers like silicon nitride and annealing under magnetic fields to optimize magnetic properties.
Sensor sensitivities range from about 0.15 to 0.17% per Oersted, though this decreases under external vertical magnetic bias fields applied by permanent magnets.
The nanoparticles used have magnetic moments sufficient to cause detectable resistance changes, as labeled bacteria flow through microfluidic channels, fabricated in PDMS, and bonded to the sensor chip.
Sample preparation is critical. Surfactants reduce fat globule size. Heating and agitation homogenize the milk, improving nanoparticle mobility and labeling efficiency.
The readout electronics include multi-channel printed circuit boards interfacing with 15 spin valve sensors, each connected to amplifiers with gains around 5,000, bandpass filtering between 300 Hz and 10 kHz, and digitization at 50 kHz sampling frequency.
Noise from the syringe pump and milk matrix can be challenging, with noise levels increasing during pump operation. Specialized training is needed to interpret data reliably.
But the magnetic detection approach offers unique advantages in complex biological samples, reducing false positives and background noise compared to optical or fluorescence methods.
That's a solid foundation. Now let's talk about giant and tunnel magnetoresistance sensors, GMR and TMR.
Sure, GMR sensors consist of two ferromagnetic layers separated by a conductive spacer, typically copper, with magnetoresistance ratios between 4 and 20%.
TMR sensors are similar but replace the conductive spacer with a thin insulating tunnel barrier, like aluminum oxide or magnesium oxide, achieving magnetoresistance ratios up to 200%.
Fabrication uses low-temperature sputtering or ion beam deposition, with magnetic fields applied during deposition to set the easy axis of magnetization.
Sensor designs include spin valves, magnetic tunnel junctions, and arrays arranged in series and parallel to improve signal-to-noise ratio.
Noise sources include thermal noise, flicker or 1/F noise, random telegraph noise, and shot noise, the latter being significant in TMR sensors due to the tunnel barrier.
Noise limits sensitivity and detectivity. TMR sensors have higher noise but compensate with higher magnetoresistance ratios.
Hysteresis is minimized by cross-axis magnetization configurations, and AC biasing along with external magnetic bias fields further improve signal-to-noise ratio and reduce offset.
Temperature affects resistance and sensitivity, so compensation schemes are implemented to maintain output stability, often below 0.1% per Kelvin.
Bandwidth-wise, intrinsic Mr. Sensor bandwidth is around 1 GHz, but practical bandwidth is limited by circuitry and packaging to below 1 MHz.
Applications are broad. Automotive systems like steering angle and speed sensing, space instruments on satellites, industrial current sensing, and non-destructive evaluation.
In non-destructive evaluation, GMR sensors outperform traditional coils and Hall sensors in sensitivity and resolution, detecting cracks and defects down to sub-millimeter scales.
Biomedical applications include biosensing proteins, DNA, viruses, and cells using magnetic nanoparticles, dynamic detection with microfluidics, hyperthermia cancer therapy monitoring, and even brain activity and magnetocardiography.
The versatility and integration potential of GMR and TMR sensors with CMOS technology and microfluidics make them a powerful platform.
Speaking of microfabrication, let's discuss micromechanical resonant capacitive magnetometers.
These devices detect magnetic fields by exploiting the Lorentz force on microfabricated resonant beams, which vibrate when an alternating current interacts with an external magnetic field.
Capacitive detection measures changes in capacitance between interdigitated finger electrodes on moving and fixed parts. The xylophone magnetometer design uses a clamped beam with hundreds of finger pairs fabricated using the SOI MUMP's process.
The resonant frequency is around 18 kHz, and vibration amplitude increases with driving current, reaching a few micrometers at the beam center.
Electrical characterization shows input resistance dominated by the gold layer, about 5.6 ohms below 100 kHz, and output capacitance around 6.7 picofarads.
Sensitivity depends on beam displacement and magnetic field, modeled using finite element simulations. Vacuum packaging improves quality factor and sensitivity by reducing air damping.
Frequency tuning is critical to compensate for shifts caused by Joule heating and nonlinear vibrations. The electrostatic tuning method applies a DC bias voltage between comb fingers, adding electrostatic stiffness and increasing resonant frequency.
Modeling shows frequency increases linearly with DC voltage at low vibration amplitudes, but nonlinearities reduce tuning effectiveness at higher amplitudes.
Experimental validation confirms frequency shifts up to 38% at low currents with DC bias, providing a feedback mechanism to stabilize frequency and improve sensor performance.
It's a neat way to maintain sensitivity and stability without complex external controls.
Now, moving to micro-machined inductive contactless suspension technology.
MIS enables frictionless levitation of microobjects using inductive forces generated by microcoils and eddy currents in conductive proof masses.
It's a passive suspension relying on physical properties, avoiding complex active control systems, which reduces friction, extends motion range, and lowers energy dissipation.
Microcoil fabrication includes planar coils via surface micromachining and advanced 3D microcoils using SU-8 pillars and automatic wire bonding.
The 3D microcoils allow many turns with fewer masks, reducing resistance and heat dissipation significantly.
Analytical modeling uses lump parameters and Lagrange-Maxwell equations to describe mechanical and electromagnetic dynamics.
Stability analysis shows coil geometry, current phasing, specifically a 180-degree phase shift between coils, and mutual inductance are critical for stable levitation.
Experimental prototypes confirm model predictions with good agreement in stiffness and stability domains.
Hybrid suspensions combining inductive and diamagnetic or electrostatic methods improve load capacity and energy efficiency.
Applications include MEMS gyroscopes, motors, and microtransporters, where frictionless operation is a big advantage.
Coil design and current control are clearly key to achieving stable, efficient levitation.
Finally, let's talk about magnetic angle sensors, which are widely used in automotive and industrial applications.
There are different sensor types based on magnet placement: through shaft, in shaft, and end of shaft.
Sensing technologies include anisotropic magnetoresistive sensors, giant magnetoresistive, tunneling magnetoresistive, and Hall effect sensors.
AMR sensors use thin ferromagnetic films and have 180-degree periodicity, limiting them to half-turn measurements without additional techniques.
GMR and TMR sensors have multi-layer structures with higher sensitivity and can measure full 360-degree rotations.
Hall sensors are semiconductor devices that, with spinning current techniques, reduce offset and noise significantly, making them robust and widely integrated.
Noise and offset reduction are critical. Spinning current techniques reduce offset to microtesla levels and eliminate flicker noise, while temperature and lifetime drifts are minimized.
Assembly tolerances, like magnet and sensor misalignment, eccentricity, and tilt, cause angle errors. The document models these effects using multiple coordinate systems and Euler angles.
Auto-calibration techniques during continuous rotation estimate and correct offsets and mismatches, significantly improving accuracy.
Perpendicular field sensors and axial field gradient sensors differ in magnet and sensor design, with trade-offs in robustness to assembly errors and magnetic disturbances.
Magnet design is crucial. Diametrically magnetized large magnets favor perpendicular field sensors, while axial field gradient sensors require smaller magnets with strong axial gradients.
Ring magnets with Farès sleeves and Halbach magnetization patterns improve field homogeneity, reduce stray fields, and enhance sensor robustness.
Experimental prototypes demonstrated low angle errors, around 0.1 degrees, with combined GMR and AMR chips inside ring magnets.
So balancing magnet size, field homogeneity, sensor layout, and assembly tolerances is key to achieving high accuracy angle sensing.
That wraps up a pretty comprehensive overview. Magnetic sensor technologies are truly interdisciplinary, spanning biology, microfabrication, physics, and engineering.
And their practical impact is significant, from improving dairy farm health and enabling frictionless MEMS devices to enhancing automotive safety.
Thanks for joining this deep dive. Hopefully it sparked some curiosity and appreciation for the complexity and innovation in magnetic sensing.
Absolutely. Looking forward to our next technical exploration. Take care.